The first property of integrals that we want to mention from section 5.4, and these are properties besides the fundamental theorem of calculus. Abstract properties of integrals. First one I call linearity. Now, this linearity can be written in different ways. And it's similar to a linearity property of derivatives. You remember that the derivative of a sum is the sum of the derivatives. d dx of f of x plus g of x is f prime of x plus g prime of x. Something similar happens with integrals. The definite integral from a to b of a sum of two functions, f of x plus g of x, can be found, if you want, by integrating f of x first, then integrating g of x, and then adding the results. The integral of a sum is the sum of the integrals. The integral of a sum is the sum of the two integrals. It also works if you use a minus sign. The integral of a difference is the difference of the two integrals. It's not so surprising when you think about subtraction as adding a negative. Though it's also related to another linearity property. The integral of a constant times a function is that constant times the integral of the function. And if the constant happens to be -1, that's like subtracting. These properties can be written in one statement that combines them both. The integral of what's called a linear combination of the functions, say c1 times f of x plus c2 times g of x, constant multiple of one function plus another constant multiple of the other function, is the same linear combination of the integrals. It's c1 times the integral of the first function plus c2 times the integral of the second function. This property, it really encapsulates the other two in one equation. And you can even generalize it further. You can do a linear combination of 3 functions or 4 functions or 100 functions or 1,000,000 functions. An arbitrary finite linear combination, and you get the same linear combination of all the integrals, the 3 integrals or the 4 integrals or the 1,000,000 integrals. Has anybody ever done an integral of 1,000,000 functions before? Maybe a computer has, no person has. Actually, in Calc 2, you sometimes integrate the sum of infinitely many functions. And sometimes integrating infinitely many functions is easier than integrating, say, 1,000,000 functions. That's the subject of infinite series. If you want to peek ahead, it's chapters 9 and 10, I believe, in the book. There are special situations. They're called geometric series and Taylor series, where doing those kinds of integrals is actually easier. It's an infinite sum. You'll have homework problems where maybe you'll be told this integral is some number and this integral is some other number, and you have to figure out that integral. Maybe you're told what C1 and C2 are as well. You just apply the property. Okay? It's abstract, you don't know what the functions are, but you're told what the integrals are. We had some abstract properties with derivatives and those kinds of problems as well, including on the last exam. At the bottom of page 1 of the last exam. These are similar. 2, this is a property that I just mentioned a few minutes ago. The integral from a to a of a function, any function, is 0. These linearity properties take proof. This property is essentially a definition. This is essentially a theorem that takes proof. There's nothing to prove here, that we're just saying that's what we want it to be. We want the answer to be 0, so we're defining it to be 0. But we can still call it a property. In a similar way, when we integrate from b to a, and we want to relate that to the integral from a to b, like we've been talking about, put a minus sign in front of them when you switch the limits of integration around. That is also essentially a definition. Nothing to prove it here. It's true because we say it's true. We're defining it to be true. If you switch the a and the b around, you got to compensate by putting a minus sign in front of the integral. With the motion and running time and backwards, that was just motivation for why this is a good idea. Why this is a good definition. Here's another important property. The integral from a to b of a function is often useful to break down into the sum of two other integrals over two different intervals. The integral from a to c plus the integral from c to b. This makes sense if you think about an example where the function is positive, a is here, b is here, and c is somewhere between a and b. What you're saying is the entire area under the graph from a to b can be broken up into the sum of two areas. The area under the graph from a to c plus the area under the graph from c to b. If f of x is positive and c is between a and b, that's how you would interpret this equation. But it's still true, it turns out, even if f of x goes below the axis, above and below, even if c is not between a and b, even if c is to the left of a or to the right of b, it still is true, though harder to interpret. It's still true, though. Where is this useful? Well, you might say it was more useful in the olden days before technology than it is now, especially in statistics. And if you take in statistics, you know about normal curves and finding areas under them as being important in statistics. We'll talk a little bit about that application next Monday. There are tables of areas under normal curves. And by their nature, tables have to be very limited in how much information is given, because otherwise there's just too many tables. Through some trickery, and I'll show you the trickery next Monday, you can use properties like this to help you find other areas besides the ones that are explicitly in the table. If you've taken some stats, you might know what I'm talking about. Maybe adding or subtracting areas under a normal curve. If you haven't, you might have no idea what I'm talking about, but I will briefly talk about it on Monday. But you should know these for the purpose of solving problems in section 5.4. There's more properties. Property 5, if f of x is an odd function, i.e., f of negative x equals negative f of x for all x, then the integral of such a function from negative a to positive a is 0. You don't have to use the fundamental theorem of calculus. And this should make sense if you think about, if you know how odd functions have origin symmetry to their graphs. For example, here's a generic odd function graph. Symmetric about the origin. Take any point on the graph and look at its reflection to the origin. That opposite point is on the graph as well. And so if I integrate this from negative a to a, the positive area over here cancels out with the negative contribution to the integral right there. You get 0. This is very useful, especially in application to something called Fourier series, which has applications in lots of areas of physics. Thinking about what are called partial differential equations for wave motion, for heat conduction, Fourier series are really important, and to do Fourier series, you have to do a bunch of integrals, often of even and odd functions. And when you do have an odd function, you're very happy because then the integral is 0 and you don't have to do much work. You don't have to use the fundamental theorem of calculus, which is a great time-saving device. It's also a time-saving device even for even functions. If f of x is an even function, so f of negative x equals f of x for all x, it's still nice, but not quite as nice as the odd function case. Then the integral from negative a to a of the function can be found by doubling the integral from 0 to a. That doesn't save quite as much time as the odd case, but it does save a little bit of time because it's nice when the lower limit's 0, oftentimes, right? Because then when you use the fundamental theorem of calculus, oftentimes you end up subtracting 0. Not always, but oftentimes. An even function, generic graph, has symmetry about the y-axis. Maybe it looks like this. And when you integrate from negative a to a, the total area under the curve is double the area under the curve from 0 to a. Double the area to the right of the y-axis to get the total area on both sides. It does need to be from negative a to a in both of these cases. But that is common in Fourier series. Final property to mention today is number 7, say, if you've got a function that's between two values, call them little m and capital M, for all x in the closed interval from a to b, the conclusion is then, even if you can't figure out what the integral is, you can say it's between two numbers. You can say it's between little m times b minus a and capital M times b minus a. And that makes sense if you think about a picture as well. If little m is right here and capital M is right there, by saying this is true, you're saying the graph of the function is always between those two horizontal lines. So the area under the curve has to be between the area of this rectangle, m times b minus a, and the area of this rectangle, capital M times b minus a, is what this is saying. There is one more thing, two more things actually, that I haven't had time to mention, but you should read about it, and I think you can get them. They also show up in the problem solving video. There's something called the average value of a function. You should look up the formula for how to compute it and how to interpret it geometrically. And also there's a description of how to find the area between two curves. You essentially integrate the top curve minus the bottom curve. Haven't had time to mention those today. It's time to end, but they're in the section as well. Okay? And you have problems about them. Have a good day.